So today we will be reviewing all the topics you will need to know for Unit 6 of AP Physics 1, which is simple harmonic motion. So to get started, there are some formulas you need to remember, and these are crucial in solving problems in this unit. And they, of course, are period of a spring, which is period as denoted by T sub S is equal to 2 pi times the square root of the mass of the oscillating object times K, where K is the spring constant. Alright, and now the second formula you will need to remember is period of a pendulum that is oscillating at less than 15 degrees. As you know, we must follow the small angle approximation. And this is denoted by period sub P is equal to 2 pi times the square root of the length of the string divided by the gravitational constant, or the strength of the gravitational field. So this will change depending on what planet you're on, because if you think about it logically, the stronger gravity pulls, the quicker the pendulum will oscillate, right? And if the string is longer, then it will take longer for the pendulum to oscillate. And now I should mention here that the last formula you need to know is obviously just your spring constant formula, which is F spring, or Hooke's law, is equal to negative K, as denoted by the spring constant here, times the displacement. And this is what helps us prove that. And I won't be doing that today, we'll just be going over some problems, but it's important that this only works with an ideal spring. So with these three formulas out of the way, if you need, you can screenshot this. We will get started on some problems. The first important problem you will need to know how to solve are graphing problems. So basically, these are conceptual problems where they give you a graph. So take the following graph, for example. So in this graph, this is of an oscillating spring on a horizontal surface. So it looks something like this, with mass m. But the question is going to look something like, given this graph, find what point has things like the position that has the most spring potential energy, the greatest velocity, or the largest acceleration. So if we just go through these three, it's pretty easy. So the most spring potential energy is always at one of the amplitudes, or one of the endpoints. So here the answer would be B or C, as spring potential energy, as if you remember, is not a vector, so direction does not matter, which means both points will be applicable as an answer. Now, as for greatest velocity, if you've taken some sort of calculus, it's pretty easy. You just have to find out which part has the steepest slope, right? But if you haven't taken calculus, the easy way you can remember this is the greatest velocity always happens at the equilibrium point, which is given as A here. So that's that answer. And then the greatest acceleration. So once again, if you've taken calculus, this is pretty obvious to see that it would be at an endpoint. But if you haven't, it's good to remember that an acceleration is usually greatest at one of these endpoints. Because if we think about it, let's draw a velocity in green, right? So this is our negative maximum velocity, positive, and then velocity 0 here. It looks something like this, right? So if this is our velocity, then if we draw our acceleration in this reddish color, we're going to notice that it's going to look something like this, right? And then acceleration 0 here. And the keen-eyed among you will notice that these are just cosine sine waves, which are derivatives of each other, which happens to be really nice. So usually, maximum acceleration for these simple harmonic problems is going to be at the maximum displacement. So it's going to be at here B or here C. All right, let's move on. All right, so this next problem we're looking at is an ideal spring with K, so spring constant, equals 20 newtons per meter, is set up horizontally with a 1 kilogram mass on the end. It is pulled 0.4 meters from equilibrium on a frictionless surface. Find A, its maximum acceleration, B, its maximum velocity, and C is period. So the very first thing that I'd like to do when it comes to these problems is just draw it out. It's nice to visualize. So if here's our spring, and then let's just say we have our block of 1 kg, and then here is the spring, and it gets pulled like this, 0.4 meters, and it's going to oscillate between this point and this point. And it's good to know that it's also going to go back over this way, 0.4 meters. So that's just how simple harmonic motion works, so that's pretty easy. Anyway, to find its maximum acceleration, remember that the acceleration of any mass, I should mention that this spring has negligible mass, but the acceleration of any mass is F equals ma, right? But also, remember, the force of the spring is a restoring force given by negative kx. So, in this case, we can find A as equal to negative kx over m. And these are all variables that are actually given, so we should probably write these variables out. So if I just move this over here for now, let's write out our variables. We have m is given as 1 kg, my bad. We have change in x, or amplitude / displacement, is equal to 0.4 meters. And then we also have k equals 20 newtons per meter, very different than newton meters. So that means we can easily solve this equation for A if we just plug in some variables here. So we have 20 times our displacement, which is 0.4, and then over our mass, which is just 1. And if you solve this out, this is just going to give A equals 8 meters per second squared. So for part A, that is our answer. Alright, moving on. Part B is asking for its maximum velocity. So if you remember, maximum velocity is what occurs through the equilibrium point. And this actually requires us to remember our energy formulas. So if you remember, our kinetic energy is equal to 1/2 times mv squared, where m is the mass of the mass, and then v is obviously its velocity. But notice that Ke maximum, so if we have all kinetic energy, this is going to be equal to potential energy maximum, which is given by 1/2 Ka squared, where A is equal to the amplitude, which is equal to x max, which was given as equal to 0.4. So we can actually solve for this by setting 1/2 mv squared is equal to 1/2 Ka squared, and solving for v gives v squared is equal to Ka squared over m, and then you can square root both sides. So this will give v is equal to square root of Ka squared over m. And solving for this by plugging in gives square root of 20 times 0.4 squared. And I should remind you guys that don't forget your units, but I'm just foregoing them for the sake of simplicity. And then mass is 1, which is really helpful. And then solving for this, just 1.789 meters per second for our maximum velocity. And now lastly, it's going to ask for its period, and this is pretty easy as well. So part C, remember, a period of a spring is given by T is equal to 2 pi over the mass, or the spring constant, because if you have a stiffer spring, it's going to oscillate faster. Bigger mass, it's going to oscillate a little slower. So it's pretty obvious. This works out. And this is just an easy plug-and-chug type of question. You're really lucky to get these on tests or AP exams. So this is going to give us 1 over 0.4, and solving gives us 9.935 seconds. Alright, and that's every part of this answer. Every part of this question answered. And that went through a lot of good topics. So let's move on to the next question. So for this next problem, we have a vertical spring that has a hanging mass of 2 kilograms. And we are given that the spring constant, K, is equal to 10 newtons per meter. Now the question is, how far does the spring stretch? And this is really easy to figure out, as we can just write, remember, the force of gravity is equal to mg, right? But this force, since the spring is perfectly at rest, this means that this force is equal to the force of the spring, which is going to be equal to kx, which actually is going to not need the negative sign this time because it is positively opposing this gravity. So from here, we can actually just figure out how far the spring stretches. X is equal to mg over k, and this is a really simple plug and chug once again. So this is going to give us 2 kilograms times, I'm going to just put 10 for the sake of simplicity, 10 meters per second squared, g equals 10, over k, which is 10 newtons per meter. And this will actually all cancel out really nicely to give us 2 meters of stretch. So this is a pretty stretchy string that is under a lot of weight, but hey, if it works, right? All right, we'll do one last problem before heading out, and we'll get to that right now. All right, a block of mass 2 kg is hung from an ideal spring with spring constant K of 40 newtons per meter. If it is then stretched 10 centimeters and released, it exhibits simple harmonic motion, and find its resulting frequency. So this does seem a little complicated at first, but always remember the formulas. Trust in the formulas. So remember, period is equal to 2 pi square root of what? Mass over k, right? So if t is just equal to 1 over f, then we can just flip this around to give us frequency, because they are reciprocals of each other. So therefore, frequency is equal to 1 over 2 pi times the square root of k over m. And it may seem like the oscillations are affected by gravity, right, in this case, and we must take that into account for our calculations, but actually, gravity conveniently cancels out on both the up and the down, so when finding frequency, we can once again plug and chug. So the really nice thing about Unit 6 is that there's a lot of plugging and chugging, so that's really nice. So if you have a good calculator and quick fingers, it'll be just fine. So if we just plug and chug our numbers here, we get 1 over 2 pi times the square root of 40 over 2 kg, and this will give us 1 over 2 pi times square root of 20, and this will give us 2 rad 5 over 2 pi. Just cancel these out, and you just want to get it simplified as much as possible until you plug into the calculator. And this will give us a frequency of 0.7. So this is our frequency, and it's obviously to the negative second. So this would be in hertz. Alright, I know that I said that was the last problem, but we do have time for one more, and I think this is actually really interesting, and it's quite important because it involves energy and vertical springs. So let's get with it. So, a spring is hung with K equals 15 newtons per meter vertically with a 50-gram mass attached to it. So first, let me just write out some variables that we would like to know. K is equal to this, and then we have mass is equal to 0.05 kilograms. Always convert to the standard units. And then it is stretched 7 centimeters, so we have D is equal to 0.07 meters, or change in X, doesn't matter. And then it's released. What is its velocity traveling through the equilibrium point? So this does seem a little more complicated, but once again, it's nothing a little math can't help. So here is our hanging mass, and then it's stretched a little bit and released. So if this is our equilibrium position, and here is where it is, it's going to also oscillate this same distance above. So it's going to oscillate something like this. So from here, I would like to define that the lowest point it reaches, which is here, is defined as H equals 0. So our potential energy is going to be 0 from gravity at this point. And now continuing, we should probably write out our energy formulas. So recall that if we are at the bottom position, there is no gravitational potential energy, right? And the entire mechanical energy of the system is in the spring. So therefore, at the bottom, we have all of our energy is equal to 1/2 kx squared in the spring. And from here, remember that at the very top, there's no more spring potential energy, and it's all gravitational energy. But thankfully, we actually don't even need to worry about what's going on at the top. We only need to worry about what's going on at the equilibrium position. And remember, we defined that the distance it pulled down was 0.07 meters, which means h is actually going to be equal to this value because of what we set as 0. So we know that total energy is going to be equal to some sort of kinetic energy. There's some kinetic energy, right? Because the mass, it must be moving through the equilibrium point. Then you also need to add its gravitational potential energy. And this is actually really nice because we found our h, we know m, we know k, and we know x. So it's actually really easy to solve for v in this case. So from here, we're going to look at how to solve this. Obviously, we should probably start by plugging in values, right? Or more specifically, we should probably just rearrange some values here. So we can first multiply everything by 2, right? But actually, if you want to deal with this in terms of just multiplying it out, we can actually do that because remember, all of these are in joules. So we don't really need to worry about units. So why don't we just do that? So 1/2 times 15 times 0.07, because we defined that right there, equal to 1/2 times the mass, which is 0.05, times v squared plus 0.05 times 10, I'm going to use 10 for this simple calculation, times 0.07. And from here, we just got to simplify some stuff. And this gives 0.03675 equals 0.025 v squared plus 0.035. And obviously, we're just going to do some rearranging. So we're going to subtract the 0.035 from both sides. And this is going to give that we have 0.00175 is equal to 0.025 v squared. So v squared is equal to 0.07. V is going to be equal to 0.2646 meters per second. And that is our answer. Now, I do have a little bit of an extra question that I would like to ask, which is, what is the total change in kinetic energy from its slowest moving point to its fastest moving point? And I'll leave that as a question for you guys to answer, just to think about. So basically, we know its slowest point is going to be at the bottom, right? And its fastest point is going to be here. So all we really need to find is this value. So that should be some pretty easy plugging in. And I hope everyone has a great day. All right, thank you for watching.